So in my last video, what I did was I whizzed through all of these circle theorems and said how they work. But in this video, I want to simply talk about how to describe them properly in an exam, because you often are asked to do that. They usually have the phrase, give a reason at the end of a circle theorem question. Give a reason for your answer. And what that actually means is you describe one of the circle theorems, maybe two, depending on how many marks it is. You usually know how many marks are given to a given question. So if it's 1 mark, just use one circle theorem in your description. But you have to use the right descriptions, and that's what this video is all about. So let's talk about this circle theorem here. Angles in the same segment are equal. So what is a segment? A segment is a piece of a circle separated by a chord. So a chord is just a straight line from one side of the circle to the other. There's a chord, there's a chord. So if this is the chord we're talking about, here's one segment and here's another segment on that side. So one segment on this side of the chord and another segment on the left side of the chord. Here's a dotted line, which is also a chord, and you've got a tiny segment on the left side and a massive or major segment on the right side. So what this one is saying, this description is saying that if you have two angles on the same segment, okay, and there's a couple of things implied there. They're not only in the same segment, but the angles are both touching the circumference, and also both the angles have a base on the chord that makes the segment. So can you see this angle and this angle both have their base on this dotted chord? So if that's true, there are two or more angles in the same segment, as it says, those angles will be equal. Now, that's a weird description, and I don't like too many weird things because they're hard to remember, they don't make sense, and in an exam, under the pressure, you're going to forget. I don't like people memorizing stuff, so there are alternatives you can use. So let's give you a quick description that you can use if you find it easier, and that is, if you have two angles on the circumference is just a quick way of saying on the edge of the circle, and when you're writing stuff down, it definitely is a bit quicker, really. Okay, so if you got two angles on the circumference of a circle, on the circumference I should just say, and their bases are subtended by the same point. So this is one hard word. Subtended is a proper English word. It basically means anchored down by. So you can imagine this angle is anchored down by this point and this point, and so is this angle anchored down by the same points. Okay, so if you have two angles on the circumference subtended by the same 2 points, they will be equal. Okay, so you can either use this standardized syllabus description or the other one that I just gave you. Both will be fine. You'll get the marks. Here's another circle theorem I want to talk about. So we've got this description. The angle subtended by an arc. Okay, so here's an arc that anchors down both these 2 points. So the angle subtended by an arc at the center of the circle is twice the angle subtended at any point on the circumference. So this angle here at the center is twice the angle at the circumference, and as long as they're both subtended by the same arc. So here's an arc. Arc is a piece of the circumference, piece of the edge of the circle, and is anchoring down this angle and this angle. They're both subtended by the same point. What's a quicker way that's also acceptable, and will give you the marks definitely, is, and this is really short, the angle at the center is twice the angle at the circumference. Great, so short, it makes sense. The description isn't perfect, but it's on the mark schemes. Mark schemes are the way examiners are told to mark exams, right? Examiners? Yeah, the people who mark the exams, those people. They follow the rules which say that's okay. The angle at the center is twice the angle at the circumference. Next one, nice short description, and uses the same kind of assumptions as this one. It says the angle in a semicircle is a right angle. So Basically, when you say an angle in a semicircle, it means, like over here, the angle is at the circumference, and it also means this base is at the edge of this semicircle, like this. These angles were, their base were at the edge of the segment that I was talking about. So anyway, the angle in a semicircle is a right angle, is what it means. You can use your own description again. You could say, if you have a triangle with one side as a diameter and the corner and the remaining corner is touching the circumference, that corner opposite the diameter is a right angle. Or you could say, in a more, let's say, succinct way, so a triangle with a base as a diameter will and all three corners touching circumference, the angle opposite the diameter will be right angled. There are even better ways, like one more way, a cyclic triangle just means a triangle with all corners touching circumference, with one side as a diameter, will be a right angle triangle. Anyway, let's move on to the next one. Here's a cyclic quadrilateral, a four-sided shape with all corners touching the circumference. The opposite angles will be 180, some to 180 degrees, gosh. Anyway, so basically, these two add up to 180 degrees. That one, there isn't much to talk about. You really do have to use the word cyclic quadrilateral. It's a very nice way of describing things, and it kind of makes sense, right? A quadrilateral that is stuck in a circle. Let's go to the next one. Again, pretty easy, so you don't really need an alternative. A radius meets a tangent at 90 degrees. Yeah? There's a tangent. A tangent, you got to know what that means. It just means a straight line that touches a curved surface. So there's a straight line that touches a curved surface. If the radius meets that tangent, then they will be at 90 degrees, and it kind of makes sense. Just try to imagine different tangents. So imagine a tangent following where my arrow is, and then as that tangent would meet about there. If you go make a radius towards the center, you can see it meets at 90 degrees. Anyway, this is more about talking about the descriptions rather than the rule itself. Tangents from an external point are equal in length. This one's really crazy, really horrible. You can use it to get marks, but you probably won't remember it. So here's an alternative. If you have two tangents, okay, the points at where they meet the circle to where they meet each other, the distance, from where they meet the circles to where they meet each other are equal. It's a bit of a mouthful. I'm trying to keep it short, but it makes a bit of sense. If you have two tangents, the points at which they meet the circle to where it meets they meet each other are equal. So basically it's saying this length is equal to this length. Anyway, if you go to a copy of my book on my website, you'll see some of these alternative descriptions I'm giving you. Anyway, this one doesn't really need an alternative description. Alternate segment theorem, or just those three words are enough. Okay, it's not too much to remember. Alternate, but it's worth explaining it. I mean, you've heard about segments already, so, but again, it's a really weird description. This is a chord, or there's loads of chords, but this is the chord we're talking about, because here's an angle in one segment, here's an angle in the other segment. It doesn't even fit in the other segment, does it? Because it goes all the way out of the circle into the tangent. So some of these standardized descriptions are really crazy. But anyway, the point is, alternate means the other segment. Okay, so if you got an angle here, the angle in the other segment is equal to it, right? So this could have been an angle in the other segment, but these crazy descriptions, that's how they work. Let's leave it alone. It's good enough just to memorize those three words: alternate segment theorem. Okay, lastly, The perpendicular from the center of a circle to a chord bisects the chord. It's not so bad. Basically, it means a line that's perpendicular to a chord from the center. So that line, it's perpendicular, i.e. right angled to the chord, and it's also from the center. Basically, we'll bisect the chord. We'll cut this chord in half. That's what these dashes are. It just means this length is equal to this length. So you could say that, or you could say a bit more easily, a line from the center to a chord bisects the chord, cuts the chord in half, if it meets at 90 degrees. I think that's a bit easier.